Hello everyone, I'm Dr. Sri Banerjee, adjunct faculty member for Ross University School of Medicine, and providing the behavioral sciences lecture virtually, and this is a recording. We did go over some foundational basic concepts regarding epidemiology, and we had a whirlwind tour of understanding the basic definitions of epidemiology and relating them back to some of the calculations and differences in incidence, prevalence, and what that means in terms of epidemiology. We also did go over some calculations in terms of odds ratio and relative risk ratio, but we will delve deeper into these and go over some of the examples. And you can always reach out to me if you have questions. So let's get started here. The 4 levels of measurement, these are very important to consider because when you're doing a study, you want to see that you're taking into consideration the type of variable. These are the learning objectives for a statistical test. Identify whether the methodology is used with independent or dependent variables. Identify the levels of measurement the independent and dependent variables have. Recognize the most common types of studies where the methodology may be used. And then we went over null and alternative hypotheses yesterday, but given a hypothetical study, associate a statistical test or epidemiological measure with the scenario. And then define bias as it applies to epidemiological medical research. And then identify some of the most common forms of research bias and discuss strategies to prevent them. So we did go over this definition previously, but the study of the distribution and determinants of disease frequency in human populations have to do with not only distribution and determinants, but also understanding frequency. So when we're thinking about frequency, there are 8 components that you want to be thinking about. One of them is how you would be classifying and categorizing disease. The idea is that if you categorize in an adequate way from the start, then you don't have to think about what the categories are going to be. And sometimes this is challenging. I'm just going to tell you right off the bat, because you want to make sure that you're selecting categories that are sensible. I'll give you an example. Age. I always get the question from many of my doctoral students that how should age be divided? And there's several answers to that. One of them is what makes sense within your study. Is that a major predictor variable? Is that a major independent variable? And then what makes sense to your study? So if you're just looking at a certain age group, then you may have to divide that up even further than what you anticipated. Anyway, that's an example. But different disease frequency, deciding what constitutes a case of a disease in a study, finding a source for ascertaining the cases, defining the population at risk of disease, defining the period of time of risk of disease, obtaining permission to study people, making measurements of disease frequency, and then relating cases to population and time at risk. All of these things you want to make sure and cover when you're thinking about disease frequency. So when you're conducting studies, studies are conducted in an attempt to discover associations between an exposure or risk factor. And time is where, here time actually matters, and I'm going to get into that a bit later. but you want to discover associations between an exposure or risk factor and a health outcome. So just drawing this quickly and understanding what this means. We can take a look here, and so you have an exposure. Say you have an exposure. Well, the exposure is leading to an outcome. So this is how you should be thinking about this. And when you have an exposure and an outcome, this main relationship should be explored further. I know my handwriting is not all that great when you're when I'm writing here, but you get the point of what I'm trying to show, and that is that that exposure and outcome are related, and if you draw an arrow, you're trying to understand how the two are connected. So just understanding, again, the normal distribution curve, I went over this yesterday. It's a Gaussian distribution. And this is actually a standard normal distribution. And so the mean, if you go one standard deviation from the mean, then you are accounting for 68% of the data. Now, if you go 2 standard deviations from the mean, that captures 95% of the data. And then if you go 3 standard deviations from the mean, then that's 99.7% of the data covered. What this means is that you have a steep peak, but then as you go on both sides, this becomes gradual. So what are the types of variables? Anything that is measured or manipulated in a study or investigation. The types of variables, there's an independent variable, and I like to say predictor variable versus outcome variable. I personally like this terminology because it doesn't require you to try to flip terminologies and understand. So here's independent variables are predictors, and dependent variables are outcome. Just remember that. So dependent variable, outcome, independent variable is predictor. Got it? Now, outcome variables versus predictor variables. Again, independent data is, what is it? And if you said predictor variable, you were correct. Unrelated data, different groups, more commonly used in research. Dependent variable is the outcome variable, so some patient or some groups versus those that are not in that group. Related paired data, and then pre-test, post-test studies. These are different types of dependent variables that are available with different methodologies. So the levels of measurement, again, I told you this was something that is extremely important, and important to differentiate between nominal, which is all categorical. For instance, sex is a very important categorical variable, male versus female, and understanding there's other categories as well there, but regardless, it's still categories that you're looking at the nominal level. Ethnicity is another one, presence or absence of disease, race. So there's no value in order. This is, again, an important concept as well. So if you designate Caucasian, say, in ethnicity as 1, and then African American as 2, this does not mean that one race is better than the other. It just means that the coding that you designated is designated to the ethnicity. Now, the one designated to Caucasian and 2 designated African American does in no way mean that one is superior than the other. And that's the difference between nominal ordinal. Ordinal, the ranking matters, the order matters, and it's not necessarily numbered. So that's not the only levels of measurement you have to worry about, but I think it's important to distinguish between a nominal variable and then an ordinal interval ratio variable. And I'm going to show you why these are more connected, the ordinal interval ratio than the nominal variable. In interval, you have data that can be ranked, but 0 does not represent absence of the characteristic. So like intelligence quotient, altitude, temperature, and all of these can be, and possible values across a continuum can all be interval data. And then ratio, it's a quantifiable and measurable product. It's the highest level of measurement. 0 is absence of characteristic. Ratios variables can be made. Height, temperature, the temperature at which molecules cease to move. So there's many possible values across the continuum. And honestly, interval versus ratio, these are, as you go from interval to ratio, there's more and more types of values that you can include. So looking at choosing an appropriate statistical test. It's oftentimes difficult to try and, according to your hypothesis, even though important, but according to the hypothesis, to distinguish between an outcome variable and predictor variable. However, with that said, it's important to be able to identify the types of variables as the dependent variable and independent variable early on in your study. So for instance, when you're looking at interval ratio versus nominal categorical, what's the time on this? UNIS is more than one outcome. Are they paired or related? All of these questions matter to understand. What is the variable type for the independent variable? Interval ratio versus nominal categorical. So you have one group, 2 groups, more than 2 groups. For 2 or greater than 2 groups, independent paired. Any other covariates, confounding factors. So I went through a lot of information within this slide, but what is important to understand is that 2 things. One, how does the dependent variable, how can you characterize it? Is it interval ratio, nominal categorical? And then what is the variable type for the independent variable? So you're just trying to understand a little bit more about dependent and independent variables. That's the main gist of this slide, and understanding, are there factors, covariate factors. So statistical methodology, how many are there? As you can see, there are quite a few. What I'll highlight are the ones that I feel like I use very frequently in my studies. One of which is very frequently used in a categorical versus categorical context is chi-square. But that's not the only place. Sometimes and of course an odds ratio is very common. Regression is very common. Repeated measures is not used often. Now, if you're talking about Pre-post-test studies, there might be a need for repeated measures. One of what I'm going to tell you is this. One of the individuals that I was tutoring a while back had an issue with not identifying which pair belonged with which pair. And because there was no notation as to what was before and after, who answered before and after, the analysis was not able to be run. So we have to watch out. You have to watch out for that. There's perils in using any of these tests. Pearson correlation I've used pretty frequently. Of course, relative risk is important too. So all of these are important, but there's ones that you use more often, others that you don't. Let's go through so remember this: case control, odds ratio, case control, odds ratio, case control, odds ratio. So when you're thinking about the calculation or equation for odds ratio in case control studies, you multiply A times D over B times C, and that's the odds ratio. So when you're calculating odds ratio, again, you can use the formula, and this is how you would use it. Here's a 2x2 table, and I said A, B, C, D, A times D, and that's 1063 times 711, over B times D, which is 1388 times 319. So that amounts to 1.71. Now, relative risk is predominantly used in cohort studies. Very important. You might be given the makings of a cohort study within the USMLE and then asked to indicate which measure of association is most seen. So the ratio of incidence of disease in the exposed divided by the corresponding incidence of disease in the unexposed group. So exposed incidence of disease and unexposed incidence of disease is relative risk. So here's relative risk, A over A plus B, and so that's 380 over 1063. Well, A over A plus B, I stand corrected, is 380 over 380 plus 683, which is 1063. So 380 over 1063 divided by 94 over 319. And when you get to that, you can see the relative risk. You can divide that up and take a look what that is. So confidence intervals and p-value. Now, how do they relate? So a rule of thumb: when the confidence interval does not include 1, and this is with relative risks and odds ratio, when they do not include 1 within the confidence interval, then you know it's significant. Now, if it were to include 1, then you would know the p-value is not significant. So these are rules of thumb which are important to take into consideration. Significance here means p less than 0.05. Attributable risk. Attributable risk gives you the value for number needed to treat. So the incidence in exposed minus incidence in unexposed. This can be calculated easily, and this is a subtraction. So as you can see, 45 divided by 130 minus, instead of division, 45 divided by 130 minus 209 divided by 1460. So the absolute risk is 0.2029. Now the risk difference or attributable risk, the excess occurrence of severe COVID-19 attributable to diabetes is in 2029 is 2029 per 10,000. So if people did not have diabetes versus people that did, 2029 did per 10,000. So the risk difference is used to quantify the risk of disease in the exposed group that can be considered attributable to the exposure by removing the risk of disease that would have occurred anyway due to other causes. If there's no association between exposure and disease, there will be no difference between the incidence rates in the exposed and non-exposed. So risk difference is 0. Number needed to treat, number of patients who would need to receive a treatment for one patient to benefit. And this is actually the reciprocal of absolute risk reduction. So the reciprocal of attributable risk between experimental groups. Remember how I calculated that? Well, you flip it on it, and we can take a look at an example. But that's the definition, and this is how mainstream physicians determine the effectiveness of a treatment in RCTs. So many physicians not only may ask you and quiz you about this concept, you're going to see this in the USMLE, and you'll see this again in the words. So this is an example of number needed to treat. 1 divided by 0.03 is 33.3. So that means that in order to save 1 extra heart attack, 33 people must be treated. And so you can actually also determine number needed to treat in different places, in different ways as well. Now on to chi-square. Now remember, chi-square, I had told you already, is one of those statistical tests which you'll be using pretty often. So when you're looking at 2 categories of, say, cognitive decline, and you're trying to see if there's an association between cognitive decline and gender. If there is, then there's a significant association. Now, dependent variables are nominal and independent variables are nominal. And you can't use this with small sample sizes. So again, the example here would be, for instance, gender and race, and see if you would be able to use a chi-square. So this is looking at 3 cohorts and the differences on age and menopause status. So NS means not significant. So when they looked at less than or equal to 50 and greater than or equal to 50, there was no significance or no significant differences among the 3 cohorts. So comparison of differences, analysis of the comparison by chi-square test. So here the chi-square test was age versus the type of tumor or breast cancer or breast abnormality that volunteers had, and others. Now Fisher's exact test, very small sample sizes. I haven't heard of n less than 25. I think the value is more so n less than 8, really low. But like chi-square is able to handle something higher. But a lot of times when you're looking at subcategory versus subcategory, the Fisher's exact test comes in handy, and it's used for researching rare diseases. So comparing means, t-test is a go-to for that. Now you need a standard, you need normal distribution for this, but sometimes even that can be relaxed. Now if there's a pre-post test, then you like to do the paired t-test and make sure you designate the same subject for each of the pre and post tests. Independent variables, two groups, dependent interval ratio. So when you're dividing that up to two groups by, like sex, then you have the need to define pre and post. So again, you have to characterize and determine what the dependent and independent variables are, and then see which ones are a better fit for nominal ordinal interval ratio according to the research question and investigation that you are trying to conduct. Now, when you're thinking about the independent t-test, comparing blood pressure by residency type would be an interesting study. And blood pressure is, in fact, we just do a mental check, a quantitative, not only a quantitative variable, but a continuous variable, and more specifically, interval. So, like for instance, compare USMLE score by specialty. That's one that is like cholesterol levels. That's continuous. Specialty OBGYN, nominal with two groups. So here's a comparison of pre and post test, post study variables, and this was the t-test that was used, and not too many were statistically significant, but breast cancer susceptibility, in fact, had statistical significance. Nonetheless, a lot of these examples are quite interesting. So moving on to the next slide. So similar to the t-test, there's 3 or more groups, independent variable, 1 nominal with 3 or more groups. Now ethnicity fits the bill here a lot better. And then dependent variable, we can still use age, so age and ethnicity. So we go into a vignette. A researcher is interested in examining the efficacy of a new antidepressant combined with a psychotherapy intervention. He designs a research study in which he assesses the effect of his treatment on self-reported levels of depression on the Beck Depression Inventory. He uses 4 treatment groups in his study design: psychotherapy only, drug only, psychotherapy and drug, and a control group. So this diagrammatically shows the groups of patients treated for depression, and then if it's drug only, drug and psychotherapy, psychotherapy only, or placebo group. So these are groups of patients that are treated for depression. It's kind of a repetition of what I said last slide. Now, two-way analysis of variance. There's also two-way analysis, but usually you have 2 independent variables. And it's used in hypothesis testing. So here, as you can see, there's a difference between one-way ANOVA and two-way. One-way ANOVA was 1 independent variable with 1 dependent variable. We're scratching that now and saying 2 nominal variables and 1 interval ratio variable. So when you're looking at, for instance, treatment for depression, you might have 2 independent variables such as gender, which is binary, and then treatment, which might be 3 levels of treatment. So in which case you can use a two-way ANOVA. With that said, there's more efficient types of ways that you can test out multiple confounding variables, or multiple independent variables predictor variables, however you want to name it, that you can test out through regression analysis. So there's an example of a two-way ANOVA, how effective is Lipitor in treating high cholesterol. And so there's the treatment group, placebo group, and then grapefruit juice drinkers, non-grapefruit juice drinkers, and then cholesterol level. So these are two groups of independent variables that is impacting cholesterol level. So then there's Pearson correlation. Independent or dependent variable should be interval or ratio, not or. Independent and dependent variable should be interval or ratio. And this is denoted by the R coefficient. Data should be independent. Describes disease in relation to some factor of interest. For instance, maybe age versus length of contraception use, or age and healthcare utilization. Assesses the strength of linear relationships. As we're talking about a positive correlation and negative correlation, so as in a straight line, as one variable increases, the other variable increases as well. Now, in a negative correlation, as one variable increases, the other decreases. And then no correlation, there's no connection between the two variables. Repeated measures design, which means that the same sample is measured at different times. And so this is almost similar to the paired samples t-test, except this is a nominal variable. And the independent variable actually becomes the time points, and then the dependent variable you only can use interval or ratio. And so this is the repeated measure design, not oftentimes used or tested, but measuring blood pressure of study participant at baseline after starting treatments and then 3 months. Good to remember repeated measures. Now to regression. Statistically denoted as R, and similar to correlation. And I would argue, R squared is also a very important predictor, model diagnostics. However, R is used for hypothesis testing and making predictions, as I said, predictive analysis. So you have independent variables that are interval ratio and dependent variables that are interval ratio. So this is more, let me back up a little bit and say this is more of a correlation than a regression. Now this is the fun part, because you get to go through this algorithm, and if you do it correctly, and the key here is to do it correctly, then you should be able to go through this fairly quickly. So the first thing to look at is these are the variables. Now when I say variables, I'm talking about what types of, just think of a mental note, what types of independent variables you have, what types of dependent variables you have, and try to see that you can actually jot down the level of measurement, because that is more important than the variable itself. What you can do is provide both the name of the variable and the level of measurement. So if you have two nominal variables, right off the bat, you know chi-square is your go-to. Now, if you have a small sample size, you have no choice, then you got to go to Fisher's exact. There you go. That's it. That was in the notes. Now, see how simple this is? When you have two interval variables, what do you do? Well, you have a couple of choices. One is doing that Pearson correlation in the R and seeing what that shows, and seeing that straight line. The second option, you can actually conduct a regression analysis. And even if you have a continuous variable for your dependent or outcome variable, and a continuous variable for your independent variable, and it's continuous, then you can easily conduct a multiple regression, even if some of your other variables are in fact categorical. So use regression if prediction is involved. That's not the only function of regression, but definitely one option of how you can maneuver your regression findings. Then you have one interval and one nominal. So when you have this scenario, then you can be thinking about t-test if it's 2 categories, and 3 or more categories, ANOVA. Technically, ANOVA can handle, well, we're not going to go there, but technically ANOVA is able to do 2 categories of a nominal variable. But according to this, and according to what you need to know, is that you use t-test for one nominal with 2 groups, use one-way ANOVA for one nominal with 3 or more groups. And then if you have 2 nominal interval independent variables, you just use 2-way ANOVA. One interval, one group. If you have repeated measures, if you have more than one point in time, then you can use the paired t-test or repeated measures ANOVA. We're getting through this pretty quickly, and I think it's extremely important to understand the process behind how you select an appropriate statistical test. So when you're thinking about a statistical test, the first thing that you think about is what? Well, you're thinking about the research questions, and then you're thinking about the variables, and then level of measurement, and then type of test, and then the next thing that you're thinking about is interpretation. So these are all the steps that you have to take in order to be able to determine which is the most optimal type of statistical test. Now there's a couple of steps that I skipped due to the sake of brevity. But I would go back to slide 39, the previous slide, and try to listen back and make sure that you not only know this, but are able to apply it into a clinical vignette. And these are all clickable links as well, so you can go into these. So now an example, you're looking at the perceived quality of life in major urban areas. Representative population samples are carefully constructed with approximately 1,000 respondents per urban area. Quality of life in this study is assessed as a continuous measure ranging from 0 to 100. One specific analysis compares the mean perceived quality of life scores for study samples in 2 cities, New York and Miami. So just be thinking about what type of statistical test is most appropriate in this scenario. Do you think it's odds ratio? Chi-square, t-test, regression? If you answered t-test, then you were correct. And the reason being is that there were 2 groups and then one continuous variable as the outcome variable. So now we'll talk about bias, factors that impact measurement. Bias is a systematic error, not a random error, systematic error in a study resulting in an incorrect estimate of the association between exposures and outcome. So this could be introduced throughout the research process, planning a study, recruiting participants, selection biases, collecting the data, and interpreting the results. So these are all levels and portions where bias can kind of bleed into. Types of bias, you might be tested on some of this. Selection bias, You're not truly selecting a sample that is representative. Measurement bias is that information is gathered in a distorted manner. Maybe records were not very clear. And I've had this happen before with doctoral students who have worked on data sets from other countries. Recall bias, awareness of disorder after recall of subjects, or alters recall of subjects. So the respondent may have been told that they had diabetes, but since then they forgot. And then Hawthorne effect is an interesting one because the mere presence of the investigator changes behavior of the respondent. There's multiple ones here, and confounding. There's outside factors that relate exposure and outcome, but confuses the effect. There's observer bias. Observer's prior knowledge of the subjects or treatment conditions biases the observations. Lead time bias. Early detection of a disease is misinterpreted as increased survival. And that's important. Experimenter expectancy is researchers' beliefs or desires are conveyed to study subjects, or otherwise known as projection. Selection bias, this can come about from attrition, and people dropping out of the study, not participating. They may have agreed to participate, but systematically some of them decline. Sampling bias, inappropriate sampling. Bergson's bias sample is only taken from a subpopulation. So case and control may be just from a hospital and not other places. That obscures what is going on with the connections in different places. Recall bias, common in retrospective studies, and what that is the cases currently have disease and need to recall what their past exposure was, and then controls. And once you do that, this allows for an analytic consideration. So case control versus cohort studies are important and important to be understanding. Measurement bias, I went over the Hawthorne effect, which is always interesting because the mere presence of an observer can cause participants to behave change. But examples of measurement bias also is faulty equipment. And maybe the blood pressure cuff was a manual cuff, and people did not have much practice using that because nowadays it's electronic, but you went to a health fair and you don't have access to one. So that's a lot on operator error. And this is actually true. This is not an example that I'm making up. Unfortunately, this happens all too often. And then address with appropriate control group and check instruments. This is how you address measurement bias. Experimenter expectancy effects, modifying the participants' behavior through subtle cues or differences in treatment. Subjects are somehow made aware of how the researcher wants them to behave. So think about the Pygmalion effect or Rosenthal effect, self-fulfilling prophecy. And then there's the observer bias. The observer's prior knowledge to the subject's characteristics or treatment condition biases the observations. Solution, you can do the double blinding. The self-fulfilling prophecy cycle is provided. Our actions impact others' beliefs, and then that causes others' actions, and then reinforces our beliefs, and then influences our actions, and then once more impacts others' beliefs, others' actions, our beliefs, our actions. So it's others' beliefs versus the person's belief, and they kind of reflect off of each other until there's so that's a bias. And then observer bias, of course, prior knowledge affects the conditions. So lead time bias, went over this. Better screening and diagnosis make it seem like survival is increased, but measure back-end survival, stratify survival rate accordingly by evaluating severity of disease at the time of diagnosis, and then major sort of a source of bias with screening tests is lead time bias. So lead time bias, the definition is early detection of a disease is confused with increased survival. That's the main problem. Lead time bias, so you have early detection, usual time, no screening, and then death. Now, when you have ineffective screening and screening lead time, the deaths are still high. But when you have screening lead time and effective screening, then the deaths are not that high. So now confounding an outside factor relating to both the exposure and outcome confuses the effect. So for instance, a lot of people that, a lot of children recently are getting the flu. But there's also a relationship between, let's say, eating ice cream and getting the flu. So you want to control for those kids that eat ice cream and make sure that the effect that you're seeing is in fact the relationship that you're seeing rather than something else that's affecting it. So it's difficult to come up with examples, but there's others. For instance, when you are looking for, let's take diabetes and cardiovascular disease. Well, diabetes is a known risk factor for cardiovascular disease. But you want to make sure that the differences are not just due to there being differences in age. You also don't want the differences based on ethnicity, based solely on ethnicity. You want to see that these are being controlled so that the groups, even though they're uneven between the experimental group and the control group, you still have the ability to control for confounding variables. So I hope this has shed some light on confounding. As you do examples, this will make sense. Super Bowl and domestic violence. This is an example of a rate that is interesting. Nearly 1 in 5 women and 1 in 7 men report having experienced severe physical violence from an intimate partner in their lifetime. So this is an interesting picture. So what additional factors may impact this relationship? Increased physical activity can lead to decreased risk of MIs. So what this is trying to show is that even though there's a relationship between increased physical activity and decreased risk of myocardial infarction, the reality might be it has nothing to do with increased physical activity, but everything to do actually with age. So age is the reason why, because it's a lower age cohort is the reason why there's decreased risk of myocardial infarction, and not that this group had increased physical activity. So this is where confounding becomes important. So let's practice. Looking at an investigator from a pharmaceutical company, they take time to introduce herself to subjects who have been randomized to receive the company's new medication, the focus of the experimental trial. She congratulates them for their good fortune in being able to use this new medication, suggesting that they will have a very favorable experience. What bias has been introduced? So they have been randomized to receive the company's new medication, the focus of the experimental trial. So is there potential confounding going on? What do you think? Do you think this is experimenter expectancy? That she had expected So in this next example, let's take a look at this. A pharmaceutical company conducts a trial of a new medication. The data analyst notices a stark difference between the dropout rate for the new medication compared to the control group. 44% attrition on the control medication, 9% attrition on the new medication. Which bias has been introduced? Now, before we go to which bias, do you remember the subcategory? This is when you have a high attrition rate, this actually introduces something. If you answered selection bias, then you were correct. So it's not Hawthorne effect where you're influencing when you take a look. It's not experimenter expectancy. It's not observer bias. So that's the only one remaining. Now, in a prospective cohort study, this revealed a potential causal relationship between cigarette smoking and onset of liver cirrhosis, which is great. But when this was stratified, this study was stratified into two groups based on habitual alcohol consumption. No significance was there between smoking and cirrhosis. What source of bias was operating? And if you said confounding, then you were correct. And that's because there's a third variable that is actually related, and this is why this is considered confounding. So now what you're doing in a study, and this is kind of a second order question, but important to understand the thought process, and so I'm going to show you that. A study is conducted to examine objective measures of health status and perceived quality of life. So as I'm reading this, I'm going to highlight this so that you can see exactly what I'm talking about. So perceived quality of life, this is what type of variable is this? Is this a categorical variable or continuous variable? This is all you need to know, not necessarily ordinal interval ratio. If you answered continuous variable, then you answered correctly. And so when you're looking at major urban areas with 1,000 respondents per urban area, you're also looking for study samples in how many cities? It says 3 cities. So you have one independent variable here and one dependent variable. So that automatically eliminates B because that's two independent variables. Chi-square I don't think will work for quality of life because it's a continuous measure from 0 to 100, we were told. So Fisher's exact, when you eliminate chi-square, you can eliminate that. Now we have remaining t-test, which is, remember, 2 categories, and we're talking about New York, Miami, and Los Angeles, so the only one remaining is one-way ANOVA, and that is your correct answer. Hope that makes sense. So we went over this table, but I want you to take this with you. I think this is important when you're studying for your steps. I think it's going to be crucial that you know this table and make sure you put this in a safe place. This will be in this video forever. So you can revisit this and make sure you know this by heart. If it's two nominal, chi-square Fisher's exact, two interval Pearson correlation regression, one interval, one nominal t-test ANOVA, one interval, one group paired t-test repeated measures ANOVA. And now this is another way to categorize all of this. I can quickly go through some of this, but if you have data, and if it's one sample, and then if you have a dependent variable, just a dependent variable, then you can figure out the mean distribution. That's what it's saying. And if you want to do a comparison, you can also do a one sample t-test if you're trying to compare it to a value. If you know the mean and the standard deviation, you can actually run it z-test. Again, this is one sample, and then independent variable, dependent variable, the Pearson's R, which is bivariate regression. And then multiple independent and dependent variables is multiple regression. So this changes as you have independent samples versus dependent samples, and it just keeps going. And so just go through this and see what you can find, and see if this makes sense. When you have an independent variable and dependent variable that is continuous. Now, so what you should understand is that this is all continuous variables. None of this is categorical variables. So when you have a dependent variable that is continuous, ways to measure that is through mean. Now, when you have independent variable and dependent variable that's continuous, then that's Pearson's R or bivariate regression. When you have multiple independent variables that are continuous and dependent variable, that's when multiple regression works. And then multiple samples, again, through continuous variables. So if they're independent samples versus dependent samples, that's when you're using these various statistical tests. I hope that makes sense. There's a lot of content that was covered in here, different types of epidemiological concepts, statistical concepts, all combined together. If you have any questions, please don't hesitate to contact me. My email address has been provided in the beginning of this lecture, so you can refer back to that. Thank you for listening.